Okay, so last time what we did was to construct the sphere 3 and 4 point function. Okay, so let me just remind you. So we had sphere 3 and 4 point function of shell, of course. And the important part of this was that we gave a way to choose the sections, okay, such that we can express this as a sum of Feynman diagrams. Okay. And today we are going to continue this, and I'll describe how all the higher point functions can also be thought of as sum over Feynman diagrams. Okay. So let me begin with the sphere 3 point function, okay, which we had already introduced. Okay. And all the vertices are symmetric, so it doesn't matter which one is what. Okay. So this describes a sphere with 3 punctures. Okay. So now imagine that we insert a state V1 on one puncture, okay, and then we show the other two. Okay. So this is mod W equal to mod Q to the half. Okay, appropriate choice of local coordinates, mod W prime as mod Q to the half. So these local coordinates are of course fixed by this function choice of this F1, F2, F3. Okay. And then we show them together using W prime equal to minus Q. Okay. So this clearly generates a torus, okay, because you are showing 2 punctures on a sphere. And if we follow the interpretation in terms of Feynman diagrams, okay, what it amounts to is that you start with a 3 point function, okay, and then join 2 of these by a propagator. So in terms of Feynman diagrams, it certainly looks like one loop, 1 point function. So this is a Feynman diagram interpretation. And because this comes equipped with a local coordinate choice, because the local coordinate here is fixed by this F1. So what we have is a section segment of P11. Okay. So let me draw P11 again. Okay, so let me remind you, we have base as M11. So this is genus 1 point function. Okay. This is the choice of local coordinate. In this case, there's only one. Okay. And this generates some segment of a section. Okay. Again, it doesn't cover the whole region because we look at the mod Q less than or equal to 1 region. Okay, and which, if we follow this procedure of adding stubs, this is can be made into a small region of P11. Okay, but of course it's an important region because this contains the degeneration. Okay, Q goes to 0 limit is when this torus degenerates because you are basically pinching the handle that connects these two. Okay, or this line goes on shell. So as in the previous case, we now fill the rest of the region by some smoothly by some other segment of the section. This I'm going to call S prime 10. Okay, in the same spirit as last time, S prime Gn. Okay, this is so S primes are the ones that fill what is missing. Okay. And now the total contribution, total one loop 1 point function, is of course the integration over the whole section. This one you already know, its interpretation is the Feynman diagram with one explicit loop. So now you have to interpret the rest. Okay. So let me write this. So that what is the rest? Rest is GS. Okay, this comes from this 3G minus 3 plus n factor. Okay, in this case, G is equal to 1, n is equal to 1. So that's the GS. And then integral over S prime 1, 1, omega 1, 1 Okay, and it's a two form because you have a two-dimensional. So this is a two-dimensional space. So 2, and the vertex of part of that we insert, of course, is V1. Okay. So this is a contribution from S prime 1 0. This one we already know how to do by plumbing fixture. So now you have to interpret this in terms of Feynman diagram. Okay. And the Feynman diagram that we'll be using to represent this is this. Okay. So it's as if it's a explicit one-point function that you have added to the axiom. So one loop, one-point vertex. Okay. So this one you can think of as a one-point vertex. Okay, but it's at one loop. And its interpretation is that this you can think of as a one loop counter term. Okay, counter term is something that you are familiar with from quantum field theory. Okay. But normally in quantum field theory, the counter terms are added to remove divergences. Okay. Here, this has a quite different purpose. Okay. So this is added, okay, not to cancel divergences, because it's finite, actually, divergences, but for gauge invariance. So this is a finite counter term. So let me write this explicitly, a finite one loop counter term. Okay. And the way we see that this is needed for gauge invariance, okay, at least from the practical way, is that we have seen that if you want to, for example, show decoupling of pure gauge states, right, you get a total derivative on this section. Okay. But of course, the total derivative, okay, if we only take this part of the section, then the total derivative will give boundary terms from these two artificial boundaries. Okay. So the purpose of adding the rest of the section, the S prime 1 0, so is so that you don't get any boundary. Okay, you integrate over the full section. Okay, and that's the way you see that we need this part for gauge invariance. Okay, so this is important. Are there questions?
I have a question. Are we integrating over S11 or S10?
No, S11 because you still have one puncture, right? If you look at this, it's a torus, but it has one puncture.
I see. Yes. Thank you.
So S10 you don't really need because that doesn't enter any S matrix. That's like a vacuum amplitude. Okay, so those, at least from S matrix perspective, are not important.
I see. Thank you.
Okay, so with this, now it should be clear how to proceed for hard quantum amplitudes. Okay. So now we can generalize this. These to higher quantum amplitudes, higher order. Okay. And order in this case, okay, this will be an iterative construction. Let me say this is an iterative in this 6G minus 6 plus 2n. Okay. So this, if you remember, is the total number of parameters that label a genus G n-point function. Okay. And then, was there a question? The reason that we iterate in this, okay, is because we know that plumbing fixture this adds two extra variables. Variables to integrate over. And that's this QQ bar. Okay, you have to do integration over QQ bar. Okay, so when you to get things together by plumbing fixture, you increase this number. Okay, so that's why you start with the lowest value of this. In fact, the sphere 3-point function has this equal to 0. Okay. then the sphere 4-point function and the torus 1-point function has this equal to 2. Okay. Now we go to the next step, okay, which is when this takes value 4. Okay, it's always even. Okay, so for example, sphere 5-point function, okay, or torus 2-point function, okay, will be the next in line. Okay, but instead of giving doing those explicitly, I'll now state the general philosophy. Okay, how do we do this? Okay, so the way we proceed is that we pick some value of 6g minus 6 plus 2, some value of g and n. Okay. And then we first construct all the section segments obtained by plumbing fixture of lower order vortices. Okay. So lower order basically means that 6g minus 6 plus 2n is lower order, lower than the one that are considering. Okay. And any plumbing fixture, okay, will involve this with lower value, because plumbing fixture we all know that adds 2, right? So you cannot have anything larger than this or equal to this. Okay, it has to be at least 2 less than this number. Okay, when you do the plumbing fixture of lower order vortices. So these would have been already constructed in the earlier stages. Okay, like 3-point function, 4-point function, etc. And then fill the gap smoothly by S prime Gn. Okay. And then you have to give it an interpretation. So gs to the power 3g minus 3 plus n integral S prime Gn of omega Gn 6g minus 6 plus 2n. Okay. And it will be characterized by, of course, V1 to Vn. These are the external vortex operators. Okay. This has the interpretation of, from Feynman diagram perspective, this should be thought of as a G loop endpoint counter term. Okay. But again, it's a finite counter term, okay, because this region, okay, does not involve any degenerate Riemann surface. All the degenerate Riemann surfaces are obtained by plumbing fixture, okay, as some diagrams connected by properties. So let me just show some examples. Maybe it will become clearer. Okay. So for example, take g equal to 0, n equal to 5. Okay. So to do g equal to 0, n equal to 5, we first construct the lower order Feynman diagrams. Okay. So here is 1, 2, 3, 4, 5. Okay, because you have already constructed a 3-point function earlier, so you put them together. Okay, and then plus permutations, of course, plus various other kinds, others of this kind. But you also have to use the 4-point vortex that you have constructed and plumbing fixture. Okay, so this is also a lower order vortex, right? So you have to take this, say 1, 2, 3, 4, 5, and then many others, including that uses this 4-point vortex. Okay, so you add all of these. Okay, for each of these, okay, by using the rules of plumbing fixture, you can associate a section segment. Okay, so each Feynman diagram comes with its own segment of a section of P05. Okay, so you put them together, then see what is left. Okay, and whatever is left, you reinterpret the integral, the contribution coming from that as a, in this case, g equal to 0, 5-point vortex. So this will be gs square integral S prime 0, 5 omega 0, 5 Is this clear? Okay, now I should just say that this procedure that I have described is practical. So this procedure is practical in the sense that it solves what we wanted to solve, okay, which I'll now describe in a few minutes, okay, but perhaps not necessarily elegant. Because there is a lot of arbitrariness involved, right? This because each of those S primes can be chosen in many different ways, right? All we are doing is to fix the boundaries of S prime, and then we choose them to be anything that we like, consistent with symmetries. Okay. So these, of course, people have tried to make things more elegant, okay, by choose section segments with in a natural way, okay, whatever that means. Okay. So some of the names I'll just quote, for example, minimal area metric. Okay, I'll not describe any of these are just names, okay, or hyperbolic metric. These basically all correspond to choosing the section segments and the local coordinates in some nice way. Okay, but for our purpose, this is good enough. Okay, because all we need is that we should be able to organize the amplitude as sum of Feynman diagrams. Because the point is that once the amplitudes are arranged as sum of Feynman diagrams, are arranged as sum over Feynman diagrams, we can use QFT insight, including LSZ, to deal with the problem of on-cell internal propagator. Okay, so I'll try to make this a little more precise. What we mean by use QFT insight, right? And where is this construction explicitly useful? So we can look at the example of self-energy diagram. And as we discussed earlier, that naively, if you insert a self-energy diagram on the external leg, you get an on-cell internal propagator, okay, and that causes divergence. Okay, so what are you supposed to do in QFT? Okay, so in QFT, we are supposed to sum over these objects. Okay, if you call this sigma and this as a T-level propagator, so 1 over k square plus m square. Then this sum we rewrite as 1 over k square plus m square minus sigma k. Okay. And then we can try to look for the poles of this propagator and do LSZ. Okay. But what is sigma? Okay. So sigma, let me remind you, okay, even a quantum field theory, is a sum of 1pi diagrams, one particle irreducible diagrams. Okay, the diagrams which cannot be cut into two parts, okay, by cutting in one internal line. Okay, cut into two parts with one leg on each side, one external state on each side. Now, to implement this, we need to know what is the definition of one PI diagram. So, for example, in a quantum field theory, this is a two-loop one PI diagram, but this one is not. So you should include this, but not this. But if you are just having a two-loop, a genus two-point function, okay, in the worldsheet description, okay, then you have just one integral, right? You don't know how to list which one is what. Okay. And it's only by organizing these contributions as a sum of Feynman diagrams, okay, that you know which one to include and which one not to include. Okay. And this is the importance of what I described, that by organizing the amplitude as sum over Feynman diagrams, okay, you can distinguish one PI from non-one PI diagrams, okay, and then do this resummation. I should also add that this decomposition, right, which regions are one PI and which regions are not one PI, okay, this depends on the choice of S prime 0. So this is ambiguous. Okay, so this split depends on the choice of S prime Gn, okay, and as a result, it's necessarily ambiguous. Okay. But a choice has to be made. Okay, even though it's ambiguous, okay, a choice has to be made to be able to do this. Okay. And once you have made a choice, you have to stick to it. Okay, you compute this. Okay. And what is guaranteed at the end? Okay, I'll describe. I'll just mention why it is guaranteed. But what is guaranteed at the end, okay, is that while the sigma of k, okay, depends on this choice, okay, all physical quantities that we derive from here. Okay, so physical outcome, like pole position, that's the spectrum, okay, or S matrix, are independent of the choice of S prime 0 and S prime Gn. Okay, I'll not prove this, but I'll say how I'll mention in a few minutes how it is proved. But it's clear that in order to be able to even do this, okay, you need this split into what are one PI and what are not one PI. In particular, the one PI diagrams, okay, don't have poles. These one have poles. Other question? Okay, so now I'm going to state something without proving it. Okay. It turns out that these Feynman rules that we obtained can be obtained by gauge fixing a gauge invariant string field theory. And once you understand this, okay, but this, as I said, I'm not going to discuss this. But once you accept this, that these Feynman rules actually follow from gauge fixing a gauge invariant string field theory. Okay, after this, okay, all the nice results that I mentioned, like decoupling of pure gauge states, or independence of physical quantities of the choice of S prime Gn etc. follow from the usual word identities of the gauge theory. For actual computation, you don't need to do this. You don't need to know this. Okay. And you will find that when you follow this procedure and do the computation, that at the end, all physical quantities become independent of the choice of S prime Gn. Okay. The pure gauge test decouple and so on. Okay. But the explanation of that, okay, the simplest explanation of that can be given in terms of the word identities of an underlying gauge theory. Okay. But these I'm not going to discuss. Okay, so these will not be discussed. Because that will take us too far from what we want to do. Okay, so this is more or less as much as I'll say about bosonic string theory. Okay, I'm going to begin the discussion on superstring theory soon. Okay, but before I do that, let me just remind you what the issues are about with bosonic string theory. Okay, why don't we take it very seriously so that we know what to do in superstring theory, issues in bosonic string theory. The first issue is, of course, the tachyon. Okay, and this makes a theory inconsistent. Just like a tachyon in a quantum field theory will make it inconsistent. So this will be resolved in superstring theory. We'll see. The second issue, okay, is the fact that we have d equal to 26. Okay, but we live in d equal to 4. Okay. It turns out that this is not a very serious issue, okay, because this can be resolved by an idea known as compactification, by taking 22 of the space dimensions to be small and compact. Okay, just to give an example, when we can take each of them into a circle. Okay, so xi, we identify xi and xi plus 2 pi ri. Okay, for some length, for I equal to 4 to 25. Okay, so 0, 1, 2, 3 remain non-compact directions, and these become compact. Okay. An idea is that as long as r is small enough, as ri are small enough, these dimensions are not observable. So let me just say a few words about what changes in actual analysis. Okay. So in actual analysis, okay, there are two main changes. First of all, the momenta associated with these compact directions become quantized, okay, where ni are integers, positive or negative. But the second aspect, okay, is that you also now have winding modes. Okay. So what are winding modes? So recall that earlier when we had expanded our x mu in as a function of tau and sigma, we had expanded in powers of e to the I n tau minus sigma. Okay. And then e to the I n sigma came because the sigma had a period which is 2 pi. Okay, so that's why the expansion had to be in the powers of e to the I n sigma, and then the e to the I n tau came from the time dependence. Okay. But now we also have the possibility that when sigma changes by 2 pi, okay, it's not periodic, but it winds 2 pi ri omega I or ri wi, okay, where wi's are integers. Integer. So these are known as the winding modes. Okay. So these are additional states of the string which also must be included in the spectrum. Okay. So effectively what happens is that the spectrum changes and the interaction and the correlation function changes. Functions change. But we still have a CFT. CFT with C equal to 26. And all the general discussion still hold. Okay. In fact, this theory has some nice properties also, okay, which is a symmetry under the exchange of momentum and winding. Okay. And you take the radius to 1 over ri. Okay, so there is a symmetry. You can show that the spectrum is symmetric. You can already see the spectrum has this symmetry because if you exchange ni and wi and ri to 1 over ri, okay, it's not fully visible here, but it is something you can show. Okay. Then the spectrum doesn't change. Okay, in fact, you can show the interactions also don't change. So that's a symmetry which is called a T duality. Okay. But I'm not going to discuss this any further. Okay. The important point for us is that we still have a C equal to 26 CFT and we can do whatever we did in this theory. In fact, more generally, and this will be useful later, we can use any C equal to 26 CFT to construct string theory. So even you see that even though bosonic string theory is not consistent, you have many choices of a bosonic string theory because there you can have many different C equal to 26 CFT. Okay. So this is sometimes known as the landscape. Okay. And physically, we can think of this as different classical solutions of some string theory of string theory. Okay. So to give an analogy with quantum field theory, okay, then imagine that you have a quantum field theory with a scalar field, okay, which has multiple minimum, okay, or multiple local minimum. Okay. Then you can try to do perturbation expansion by expanding the action around any of those minima. And it will give a perfectly good perturbative theory. Okay. So these different classical solutions or these different compactifications can be thought of in that way. Right? That these are just different classical solutions of some underlying string theory. Okay, so next I'll turn to superstrings. Are there any questions? Okay, so superstrings. So here the starting point is that the worldsheet theory. You remember the worldsheet theory that we had for bosonic strings had diffeomorphism. Okay. Now the worldsheet theory has a diffeomorphism and local supersymmetry. But these are not the physical diffeomorphism, physical general coordinate invariance and physical supersymmetry, because these are all in 2 dimensions. Okay, we'll see the emergence of actual space-time supersymmetry later. So we gauge fix. Okay. And now the gauge fixing leads to ghosts, okay, which include the BC, B bar, C bar that we introduced earlier. Okay. But it also includes now the ghosts associated with the fixing of local supersymmetry. Okay. And those are typically denoted by beta gamma, beta bar, gamma bar. Okay. These are Grassmann even. Okay, I'll not attempt to write down the action of these because that's not very useful. Okay, we never use the action of BC, B bar, C bar anyway. Okay. I'll eventually write down the operator expansion of these objects. Okay. But first, let me say why they are Grassmann even. They are Grassmann even because the supersymmetric transformation parameters themselves are Grassmann odd. Okay. So because of this, the ghosts, associated ghosts become Grassmann even. Okay. These are Grassmann odd as well. Okay. And just like B and C were holomorphic and B bar, C bar were anti-holomorphic, a similar property exists for these. So we have del bar beta equal to 0, del bar gamma is 0, del beta bar is 0, del gamma bar is 0. Okay. So I'm not going to describe how we do the gauge fixing and arrive at this. Okay. Instead, I'll take the more practical viewpoint that I'll now write down the various identities involving these fields that will be needed for computing amplitudes. Okay. But let me first introduce all the other fields. Okay, so the matter sector. Okay. Earlier you had X mu. Okay, but that of course also has to be supersymmetric. Okay, we cannot take a non-supersymmetric matter and couple to a supersymmetric worldsheet theory, so our supersymmetric local worldsheet theory. Okay. So the matter sector now will have to have fermions. So besides X mu, we have a psi mu and psi mu bar. And psi mu is holomorphic. And psi bar mu is anti-holomorphic. Okay, now I'll describe an important property of the beta gamma system, again without proof. So beta gamma system can be bosonized. But I should also say at this stage that I'll be describing the various properties in the holomorphic sector, but identical things hold in the anti-holomorphic sector. Okay, I'll not write them down explicitly because that will just be copying the same thing with some bars put on. Okay, now this bosonized, okay, is a somewhat strange word because beta and gamma are already bosons, right? I said these are Grassmann even. So what do you mean by bosonizing beta and gamma? Okay. So let me write down the relationship. Okay, so you bosonize them, but at the same time you put some additional fermions. So the rule for bosonization, okay, is that beta is del xi e to the minus phi. Okay. Gamma is eta e to the phi. Okay. Where phi is a boson and xi eta are fermions. Again, from the worldsheet perspective, these are Grassmann odd and this is Grassmann even. And because beta and gamma are holomorphic, so are xi, phi, and eta. Okay. So you have del bar xi is 0, del bar eta 0, del bar phi 0.
Do you mean del eta e phi for gamma?
Pardon?
Is it del eta e phi?
No, it's just eta. And that's important. It's not del eta. Okay. Here there is a derivative of xi, but this is just eta. That's the rule. Okay, because if you want to see, you have to make sure that you bosonize in certain way, such a way that the properties of beta and gamma are reproduced by the properties of xi, eta, and phi, and that requires that we use precisely these rules. Okay. Again, I am not going to describe how these rules come about. Okay. But you can think of that now, instead of using beta and gamma, you can just work with the xi, eta, phi system. Once I specify the properties of the xi, eta, phi system, that automatically determines the properties of the beta gamma system. Okay. But the precise rule is this. Is this okay?
Yes, thank you.
Okay. Now, how does...
Can I ask one more question?
Yes, please.
Yeah, so you said that beta gamma are Grassmann even, but it seems like this form of beta and gamma through eta and xi are Grass odd. So
yes, okay. So just hold on for 1 minute. I'm going to describe this now. How this becomes Grassmann even.
Okay, thanks.
Yeah. So the point is that e to the q phi has Grassmann parity minus 1 to the q. Okay. This will also become clear when I write down the operator expansion. Okay. So this is despite the fact that though phi is a boson. Okay. And this is something that happens in 2 dimensions. Okay. In fact, this is, we are more or less familiar with this from the old paper of in the 70s by Coleman and others for bosonization. Okay. That even if you start with the boson, okay, the exponential of the bosonic field sometimes can act as a formula. Okay. So e to the q phi indeed has Grassmann parity minus 1 minus q. So e to the phi and e to the minus phi are both Grassmann odd. Okay. And that's the way beta and gamma becomes Grassmann even. Okay, so xi and eta are Grassmann odd, e to the minus phi, e to the phi are Grassmann odd. So beta and gamma become Grassmann even. Is this okay?
Yes, thank you.
Okay, so now let me write down the operator expansion. Of various fields. Okay, and I'll write down the ones that are new. Okay, the old ones are still valid. Okay, which were there for bosonic string theory. Okay. So psi mu of z, psi nu of w, this is something new. And this is minus eta mu nu over twice z minus w. Okay. See, a lot of these depend on the convention, right? Sometimes you'll not find this too. Okay. But that depends on how you normalize your psi. Okay, I'll normalize my psi to satisfy this. Okay. Then xi of z with eta of w is 1 over z minus w. Okay, xi and eta operator vanishes. Then phi will be normalized such that and e to the, maybe I should write the next one, e to the q phi of z, e to the q prime phi of w is z minus w to the power minus q prime times e to the q plus q prime phi of w, plus there are less singular terms. Okay. And so now you see that if q and q prime, okay, are both odd, okay, then this is an odd power of z minus w. Okay. And that means that it's antisymmetric under ZW exchange. Okay, because there is an odd power of z minus w. Okay. And that's another way to see that e to the phi, e to the q phi, and e to the q prime phi behave as Grassmann odd objects if q and q prime are odd. Okay. Now some more information. Okay. The energy momentum tensor. Okay, this describes the response of these systems when you change the background two-dimensional metric. Okay. So T beta gamma is minus 3/2 beta del gamma Okay, so based on this, I'll now, whatever I have said, I'll now leave you with some exercises. Okay. So first, find beta gamma OP. Okay, beta and gamma are given in terms of xi eta phi. Okay, you know that what the OPs of xi eta phi are. Okay, and the only thing you have to make sure, okay, and this is important, okay, if you want to be take care of all the signs, etc. Okay, that if you are taking the OP of beta and gamma, when you take del xi with eta, okay, you have to make sure that because you are moving this del xi past e to the minus phi, you pick up a minus sign because this is Grassmann order and this is Grassmann order. Okay, so those minus signs have to be kept track of properly. Okay, then the conformal diagram.
There is a mismatching in the parentheses of T phi. There is an open parenthesis that is not closed.
Yes, I should have. Anyhow, probably this parenthesis is not necessary. Yeah, it just closes here. Yeah, this parenthesis actually was not necessary. Okay, now the conformal weights. Okay, all of these can be found from the operator expansion. Okay. So xi is 0, 0, eta is 0, 1, e to the q phi is 0. The first one is always 0 because they are all holomorphic objects. Minus half q times q plus 2. Gamma is 0 minus half. Beta is 0, 3/2. And psi mu is 0 half. Okay. So one consistency check is that we can calculate the conformal weights of beta and gamma in two different ways. Okay. First is that you calculate the conformalities of xi and eta, okay, and then e to the q phi and also del phi, okay, which has conformality 1. And then you can use the formula for gamma and beta in terms of xi eta phi to find out what the conformalities. Okay. The other way is to directly compute it using this T beta gamma. And those two agree. Okay, and that's a consistency check that this T beta gamma is consistent with this T xi eta plus T phi. Okay, because beta gamma system is supposed to be the same as the xi eta phi system. Then the third exercise is to show that T psi has central charge d by 2. Okay, mu here runs from what 0 to d. Sorry, 0 to d minus 1. Write this. So mu goes from 0 to d minus 1. Okay, total dimension is d. And the fourth exercise is that T beta gamma has central charge 11. Okay. And again, T beta gamma central charge, you can calculate it in two different ways. Then once you have gotten the beta gamma OP, okay, you can directly use this. Okay. Or you can use the T xi eta plus T phi, calculate the central charge of T xi eta, calculate the central charge of T phi and add them up. Okay. And you can again check that both give you the same answer 11. Okay. So now let's see what the vanishing of the central charge tells us. The vanishing of the central charge okay. So what is the total central charge? First, let me get the bosonic ones correct. So D from the x mu's, okay, and then minus 26 from the BC. Okay, those are already there. And now you have to add up the extra ones. Okay, so plus D by 2 plus 11. Okay. So this should be 0. And you can easily check that this implies that D is 10. Okay. So total stress tensor transforms as a primary of dimension 2 in D equal to 10. Okay. And as we will see later, okay, this is also related to the nilpotence of the BRST charge. I'll define the BRST charge in this theory. And QB square equal to 0 will also demand D equal to 10. Okay, so that's why we say that the superstring theory is consistent in D equal to 10. Okay. And then in the same spirit as in the case of bosonic strings, we have to make 6 of these directions to be small and compact if you want to make correct connection with the universe that we live in. Other questions? Okay, so let me go through some more definitions. So ghost number. Let me remind you again that whatever I did for the holomorphic sector, one can repeat for the anti-holomorphic sector. Okay, that is exactly similar structure. So the ghost number I'll define to be 1 for C bar, gamma bar, and eta bar. Okay. We can do a refined definition, which is holomorphic ghost number and anti-holomorphic ghost number, where 1 will be for holomorphic one, so 1 will be for C gamma and eta, and for the anti-holomorphic one, it will be 1 for C bar, gamma bar, eta bar. But I'm just writing it at one go. This is minus 1 for B bar, beta bar, and xi bar, and 0 for the rest. And that includes these 5 fields, includes del phi and e to the q phi. Okay, so e to the q phi also has ghost number 0. Then I'll introduce picture number. Okay, and here I'll write separately for holomorphic and anti-holomorphic. Okay, so it's Q for e to the Q phi, 1 for xi, and -1 for eta, and 0 for the rest. Okay, these will become important later. Right now, it's just definition. Okay. So in particular, beta and gamma have 0 picture number. Okay, because beta is del xi e to the -5, right? So del xi has picture number. Sorry, del xi. I think I have. Yeah, del xi e to the -5. So it's 1 for xi, and e to the -5 has picture number -1. So they add up to 0. And eta, sorry, gamma is eta e to the phi. And again, the picture number adds up to 0. Okay, -1 plus 1. Similarly, anti-holomorphic picture number. Okay, so one more definition. So we'll define TF. Okay, this is only in the matter sector as minus eta mu nu psi mu del x nu. And it's the significance of this is that this is the super partner of Tx. Okay, if you make a wild seed supersymmetric transformation of Tx, you get Tf. And similarly, Tf bar. Okay. So based on this, we can define what we'll call super conformal primary. Okay. And this is super conformal matter primary in the matter sector. So matter primary. Okay, so matter basically means that it's made of X psi psi bar. No ghost. So if you call the primary V, okay, V is the operator, okay, then the condition is that the V must be a primary in the usual sense. Okay, so in particular, it's operator product with T or with Tx or Tx plus T psi will have the appropriate property. Okay, and furthermore, okay, when you take the operator product of Tf with V, it should have the structure as 1 over z minus w times some operator. Okay, let's call this p tilde w bar plus. Okay. The important point is that the maximal singularity that Tf with V operator product should have is 1 over z minus w. Okay, there should be 1 over z minus w square in this product. So this is the definition of a super conformal primary. Okay. And just to give an example, psi mu, okay, is a super conformal primary. Okay. But not del x mu. Okay, because del x mu with Tf will have a double pole. Right? Del x mu with Tf because del x OP has 1 over z minus w square. Okay, so this will have a double pole, and that's not that violates the condition of super conformal primary. Again, this definition will become important, will be useful later. Right now, it's just a definition. Okay, more definition. So GSO parity. Holomorphic sector, and again similar results for anti-holomorphic. So we define the GSO parity to be -1. So this is -1 for beta, gamma, psi mu, -1 to the q for e to the q phi, and 1 means it's, so GSO, this is a parity, this is Z2 quantum number, so it's either -1 or 1. So it's 1 for the rest. Okay. So it includes zeta and I, eta, xi and eta. Okay, and that's consistent because you can see if we use beta as del xi e to the -phi, then e to the -phi has odd parity, beta has odd parity, del xi has even parity, so it's consistent. Similarly, gamma as eta e to the phi, that's also consistent. Okay. So now an important statement. Only GSO even operators are kept in the CFT. Okay. The GSO odd operators are there, sometimes they are useful, but we are not going to keep them as valid operators in the conformal field spell. So similarly for on the left, similarly in the anti-holomorphic sector. Okay. So that is a separate projection in the holomorphic sector and anti-holomorphic sector. Because an operator to be kept, it has to be GSO even in the holomorphic sector and GSO even in the anti-holomorphic sector. Another important constraint, let's call this one, is that we keep only those operators that involve derivatives of psi, but xi and psi bar, but not xi bar themselves. Okay. Which means, for example, okay, that if you have an operator like del xi del x mu, this is perfectly fine. This is perfectly fine. Okay. But if you have xi del x mu, that's not allowed. It is not allowed. We will not keep these operators. Okay. In fact, one can easily see that if you try to use operators of this kind and then try to apply the usual conformal identities, you run into all kinds of trouble. Okay. So this is sometimes called the small Hilbert space. Okay. Sometimes people work in the large Hilbert space where you also include xi and psi bar, but we will not do that. Okay, we'll work in the small Hilbert space, which means that all operators that will be allowing are those which do not have explicit xi and psi bar. Okay. And that, in a sense, has its root in the fact that, after all, the original ghost system was beta and gamma. Okay. And we see that from this relation, okay, that the Xi 0 mode, okay, does not affect beta or gamma. Okay, because beta involves the derivative of Xi. Okay. And so Xi 0, the 0 mode of Xi, in fact, was not there to begin, right, in the beta gamma system. Okay. And then, because to reflect that, we'll make sure that we don't allow the 0 modes of Xi at all in the spectrum of RX operators. Are there questions?
Why do we not have X mu in the CFT?
Well, X mu is a different reason we can in principle have, except that X mu is not a good conformal plane. Because X mu has logarithmic growth. So that's the reason why we don't keep X mu. Okay. But it's not that if you exclude X mu from the spectrum in the way that we are using the Xi 0 and Xi, the Xi by itself from the spectrum.
I see.
X mu we can think of in a somewhat limiting sense, right? That you have e to the I k dot x. So if you take integral delta prime of k e to the I k dot x dk, okay, let's say one dimension. Okay, this is roughly like x. Okay, because you just do integration by parts. Okay, and you bring down ikx, okay, and then you set k equal to 0. Okay. So you can think of x as a somewhat singular operator, okay, defined this way. These operators are perfectly fine, right? So you are just taking appropriate linear combination of the these well-defined operators to get something like x. Okay, so you can think of x in this way. Okay, if you want to calculate the correlation functions of x, you can try to use this kind of representation. Okay. But the Xi, excluding Xi is in a very different footing. Okay, we just simply eliminate it from the spectrum of operators. Are there other questions? Okay, now I'll give an exercise. Okay. This is similar in spirit to the kind of analysis we did for the bosonic string theory to show that you need ghost number 3 from the holomorphic sector and ghost number 3 from the anti-holomorphic sector to get a non-zero correlation function on the sphere. Okay. So a similar analysis, okay, that result is still valid here. Okay, that you can so that you need ghost number 3 from the holomorphic and ghost number 3 from the anti-holomorphic sector. Okay. But we can also have similar statement for the picture number. So on the sphere, only operators with total picture number -2, -2. Okay, so -2 in the holomorphic sector, -2 in the anti-holomorphic sector. Okay. And equal number of Xi eta and equal number of Xi bar eta bar have non-zero correlation function. Okay. So you basically apply the conformal wire identities, okay, the structure of the 2-point function, 3-point function, and the asymptotic fall off to prove all this. Okay, and as I said, the strategy is exactly the kind that we used earlier. Okay. But we have to keep in mind that in applying this, okay, you should not try to apply, you should try to demand those consistencies, okay, for correlation functions involving Xi. Okay, then you will run into all kinds of trouble. Okay. For example, Xi eta 2-point function. Okay, this of course is non-zero because of the ghost. Okay, but let's just leave that aside. You will conclude that xi eta two-point function must be 0. Okay, because xi has conformal dimension 0, this has conformal dimension 1. So how can it be non-zero? Right? So this must be 0. Okay, because h xi is 0, 0, h eta is 0, 1. Okay. This argument is wrong. Okay, this is not an argument you can apply, because as I have said, xi should not be counted as a valid operator. Okay. The analog of this argument, okay, should be involving derivative of xi. Okay, so the basic object that you can start with is this one. Okay. Here, this has conformal dimension 0, 1. This has conformal dimension 0, 1. So this can be non-zero. Okay, so this can be 1 over z minus 2. Okay. Of course, this vanishes because the ghost numbers don't match up. Okay. You have to put the appropriate number of ghosts and appropriate number of picture changing operators. But barring that, okay, this can actually be non-zero. Okay, so for example, this object del xi of z eta of w, okay, and then you put c of z1, c of z2, c of z3, and then c bar of z1 prime bar, c bar of z2 prime bar, c bar of z3 prime bar, and then you have to also supply the picture numbers e to the minus 2 phi of y1, e to the minus 2 phi of y1 prime bar. This can be non-zero. Okay. You cannot apply the argument on xi of z eta of w times this. Is this clear? Okay, so this is the sense in which you should work in the, once you have decided that you will work in the small Hilbert space, okay, you should stick to the rules. Okay. There's also a way to work in the large Hilbert space, as I said, okay, but the rules are quite different. Okay, on the large Hilbert space, for example, you should have one more xi than eta. Okay, some more exercise. Using plumbing fixture. Okay, so using plumbing fixture, we can get construction of the hard genus correlation functions. So that on genus G surface, we need picture number (2g minus 2) equal number of xi eta and equal number of xi bar eta bar to get non-zero correlator. Okay, so now we have to fix the normalization just like you did in bosonic string theory, because ultimately when you talk about correlation functions, the normalization is important. So normalization. So we'll choose something analogous to what we did for the bosonic string. So C minus 1, C bar minus 1, C0, C bar 0, C1, C bar 1. And then we have to also put the picture numbers, otherwise this by itself will not give non-zero correlation function. K prime. So these are the momentum states, right? E to the I k dot x of 0 acting on the vacuum. So this is 2 pi to the 10 delta 10 I should just say here that a lot of the notations that I'm using are borrowed from the bosonic string theory, right? So anything that is repeated from the bosonic string theory, I'm not repeating here, right? So for example, this definition of the K prime, right? I had already given in the case of bosonic string theory. Okay? This is e to the I K prime dot x of 0 on the vacuum. Okay, that remains the same. Okay. I'm only stating the ones that are different from bosonic string theory. Okay, BRST current. Okay. So JB of Z, this I introduced in bosonic string theory. Now there will be extra terms. Is C times Tx plus T beta gamma. Okay, these I have defined. Plus gamma TF plus BC del C minus 1/4 gamma square B. Now this gamma square, you have to be a little careful. So it's a product of two gammas. It doesn't have any singularity, okay, because it's gamma OP doesn't have singularity. Okay. But it's still good to work this out in the language of eta phi, xi eta phi, because that's what is more useful. Okay. So let me do that here. Okay. So gamma of Z square, okay, we can think of this as limit Z goes to W, okay, eta e to the phi of W. Well, maybe W goes to Z. Eta e to the phi Z. Okay. And now we can use the e to the phi operator expansion. And then eta operator expansion, it doesn't have a singularity, but in fact it will have a 0 because they are just one odd objects. Okay. So this I'll leave as an exercise. This is non-singular. Okay, we have to do a little work to figure out what this is. This is minus del eta e to the 2 phi of Z. So if you want to write this in terms of xi eta phi system, this is what you'll get. So similarly, JB bar. Okay. And QB, as before, will be integral JB of Z dz plus integral JB bar of Z bar dz bar. And again, exercise, this is going to be a complicated exercise to show that QB square is 0 for D equal to 10. Okay, complicated but straightforward based on what I've told you. Any questions? Okay, now more definition. Picture changing operator. Okay. So chi of Z will be defined as the anti-commutator of QB with xi of Z. Okay, we can also think of this. This is the holomorphic part, so you can only use the JB. So this is a contour integral around Z of dW, JB of W, xi of Z. So you have to just basically look at the JB, the OP of JB with xi and pick up what the result is. And this is given by C del xi plus So one important point to note is that this is not in small Hilbert space. So this shouldn't really strictly make sense in the CFT that you are working in. Okay, and you will never really need to use this. Okay. So this is not in the small Hilbert space. But when I talk about operators being in the Hilbert space, I'm using the state operator correspondence implicitly. Okay. So given an operator, whether it's in the Hilbert space or not, you first construct the corresponding state by applying on the vacuum, and then it's a statement about whether that state is in the Hilbert space or not. Okay. So this is not in the small Hilbert space because it doesn't have a derivative. Okay. But chi is. Okay. So similarly, we can find chi bar. Okay. And now in exercise, check that chi and chi bar are dimension 0, 0 primaries. Okay, when I say primary, I mean ordinary primaries, not superconformal primaries. Okay, so whenever I'm referring to superconformal primaries, I'll explicitly say so. Otherwise, the primaries just means you take the OP with the energy momentum tensor and check that it has the correct form. Other questions? Okay, so now if you want to construct the complete spectrum of operators, we can follow the route that we took for bosonic string theory. So as in bosonic string theory, we can construct local operators from products of derivatives the anti-holomorphic counterpart of all this. And e to the q phi, e to the q bar phi bar for integer q bar e to the I k dot x. Okay. So just take an arbitrary combination of these, take that product, okay, construct local operators, and then you apply GSO projection. Okay, and then you subject them to GSO projection on the left and right, on the holomorphic and anti-holomorphic side. Okay. So roughly GSO projection, okay, reduces the number of allowed operators to 1/4 of what the total set was, right? Because you are applying a Z2 projection on the left and the Z2 projection on the right. Okay, so roughly it just reduces by half times half to half times half the number of operators that you started with. But it turns out that these are only 1/4 of all the operators that the theory has. Okay. This is one of 4 sectors. One of 4 sectors of the theory, okay, which is called the Nebu-Schwarz sector, NSNS. Okay. So NS here stands for the Nebel-Schwarz. So there are 4 other sectors, okay, which are called NSR. R stands for Raman, and or RNS or RR. Okay, so I'll now describe what those 4 sectors are, what those other sectors are. So we also have RNS, NSR, and RR sectors. Okay, so R stands for Raman. When string theory first started, okay, it was not even clear that you are supposed to combine the Nebel-Schwarz and Raman sector. Okay, but now we have a better understanding, and we know that the correct way to construct a consistent string theory is to combine states from the Nebel-Schwarz and Raman sectors. Okay, after you use the GSP projection. So let me describe how the Raman sector is constructed. So construction of the Raman sector. I'll describe the holomorphic sector. The similar construction will exist for the anti-holomorphic case. Construction of R sector. So the first step is to bosonize the size. Bosonize the psi mu's. Okay, we bosonize it, but first combining 2 psi's into 1. Okay, complexify. And here it's easiest to do in the Euclidean formulation, but then you can go back to Minkowski signature, psi1 plus I psi 2 as e to the I phi 1. Okay, where this is a boson. Similarly, psi 2, psi 3 plus I psi 4 as e to the I phi 2, and so on. So you get 5 bosons this way. Okay, and then we construct what are called spin field. E to the power I by 2 plus minus phi 1 plus minus phi 2 plus minus phi 5. Okay. So there are 32 such operators. Okay, because you have 2 to the 5 choices of the signs. Okay, and one can show that they transform in the spinor representation of, if we are doing Euclidean theory, then it's SO10. Okay, in the once you make the go to the Lorentzian theory, it becomes SO91. Okay, or SO91. Okay. Now it turns out that this is not an irreducible representation. Okay, this representation is reducible. Okay. And you can make it into irreducible representation by restricting the number of minus signs to be odd and even separately. Okay. So if you have even number of minus signs okay, we denote this by S alpha. This describes a chiral spinor. Chiral spinor of SO91. Okay. This chirality has nothing to do with the world sheet chirality. Okay, world sheet left and right movers are quite different. I'm only talking about right now the right movers, which are the holomorphic sector. Okay. And the odd number of minus signs okay, I'll denote them by S alpha with upper index. Okay. These describe antichiral spinors. Okay. And alpha, of course, runs from 1 to 16. Because you have 32 to begin with, but now I have divided it into 16 and 16. So the idea is that the Ramon sector states, so Ramon sector states or NSR states, let me say, Ramon in the holomorphic side, NSR states are obtained by taking products of e to the minus phi by 2 S alpha and GSO even NSNS operators. Maybe I should say operators here. Let's do everything in terms of operators. Okay, but by state operator correspondence, of course, there is a one-to-one correspondence. Okay, so you have already introduced GSO even NSNS operators. Okay, so and the idea is that the NSR sector states are obtained by taking one of these, the spin field. Okay, and you have to accompany it by e to the minus phi by 2 and then multiply by arbitrary NSNS operators. And similarly, the RNS will be opposite. Okay, so well, maybe I'll come to RNS in a few minutes. Okay, is this clear? Okay. So exercise e to the minus 3 phi by 2 S alpha is GSO even. Okay. But e to the minus phi by 2 S alpha is GSO odd. Okay. So the way one proves this, I'll just indicate how to prove this. Okay. So you see, suppose you take the operator e to the minus phi times psi alpha, e to the minus phi times psi. So let me write it here. Okay. So to prove this, take product e to the minus phi psi mu of z with e to the minus phi by 2 S alpha. Okay. This is a GSO even operator by definition, right? We have declared this as GSO even because this is GSO odd, this is GSO odd. Okay. And this, of course, is already GSO even because you are taking products with this. Okay. So to take the product of these two, e to the minus 3 phi by 2 and e to the minus 5 becomes e to the minus 3 phi by 2. Okay. Now we have to ask what about S alpha psi mu? Okay. See, S alpha, if you remember, has e to the this plus minus I phi by 2 structure, and there are even number of minus signs. Okay. Psi, a given psi, so given psi is a linear combination of e to the I phi k and e to the minus I phi k. Okay, you can write it that way, right? Because psi 1, for example, is e to the I phi 1 plus e to the minus I phi 1 by 2 and so on. Now, e to the I phi k, when you take the product with this, what it will do, right? What it will do is that it will basically, if you start the minus sign, it changes it to a plus sign. Okay. So it converts a chiral spinner into an anti-chiral spinner and vice versa. Okay. So product with psi mu and S alpha, okay, converts a chiral spinner to anti-chiral and vice versa. Okay. So that's why when you take the product of this and this, okay, you get e to the minus 3 phi by 2 times S alpha, this is anti-chiral spinner. Okay. To get this, right, you are changing the chirality but not the phi chart. You have to do the product of this with psi mu. Okay. But psi mu is GSO odd. Okay. And that's why when you take the product of this with psi mu to get this e to the minus phi by 2 s alpha, you get a GSO odd state. So by following these rules, you can figure out which states are GSO even and which states are GSO odd. Are there questions? Okay, now let me say what happens in the anti-holomorphic sector. Okay. And here there are two choices. Okay, and that these two choices distinguish between type 2A theory and type 2B theory. So type 2B string theory. Okay. We take, so now we are talking about the RNS, right? So GSO even RNS states are obtained by taking the product of e to the minus phi bar by 2 s bar alpha with GSO even NSNS. Again, let me write as operators. So this is the exact counterpart of what happened in the holomorphic sector. Okay, there it was e to the minus phi by 2 times s alpha, and you are taking the product with GSO even NSNS operators. In type 2A, here it's opposite. Here the GSO even RNS operators are obtained taking the product of e to the minus phi bar by 2 s bar alpha. Okay, so this is the antichiral spinner with GSO even NSNS operators. Okay. And these two theories are distinct. Okay. They are distinct because they are transforming the spectrum transforms differently under the space-time Lorentz group. Okay, type 2 and type 2B are distinct theories. Are there questions? Okay. So what we see is that the NSR, NSNS, these are integer spin. Of SO91. Okay, because all the vertex operators carry only the index mu and its various symmetrizations. RNS and NSR, these are half integer spin. Because on one side, it has a spinor index. Okay. On the other side, of course, it's like NS. Okay, so it has only vector index. Okay. So when you combine them, you get spinor states. Okay. So these describe physical space-time formulas. And the Ramon, okay, is again space-time bosons. Okay, these have integer spin because it involves product of a spinor on the left and a spinor on the right. Okay, so when you combine them, it becomes a vector-like a tensor-like representation of SO9, 1. So these are bosons. Okay. Now I'll just state a fact which I'll not prove explicitly, that this theory, both 2A and 2B theory, have space-time supersymmetry. Okay. I'll not prove this, but at least next time we'll see some evidence for this. Okay. So next time we'll see gravitinos in the spectrum, massless spin 3/2 state, okay. And this basically makes them into supergravity. We will also see that there are two sets of gravitinos, so one from the RNS sector, one from NSR sector. Okay. So these are really n equal to 2 supergravity and d equal to 10. Okay. Of course, string theory is much more than supergravity, right? It contains n equal to supergravity as a subsector. Okay. But besides this, it also has this infinite tower of higher massive states. Okay. But at least it will contain the spectrum of n equal to 2 supergravity. Okay. And then once you take into account interactions, you can show that the full supersymmetric quad identities are present. Okay. That makes it into an interacting theory of gravitons and gravitinos and various other particles which exist in supergravity. Okay, I think my time is up, so I'll stop here. Are there questions?
Yes, can you just quickly repeat the difference between type 2A and 2B?
Yes, so the main difference is that, in fact, the only difference is that okay, so NSR sector is identical. Okay, that's the way I have defined. When you look at the Raman sector on the right, Raman sector on the left, okay, RNS. Okay, then in type 2B, you obtain them by products of e to the minus 5 by 2 s bar alpha, where this is a chiral spinor with GSO even NSNS operators. Okay. So in particular, this operator is an allowed operator in the type 2B theory. In type 2A, the allowed operators are obtained by e to the minus 5 bar by 2 times the anti-chiral spinor, okay, multiplied by GSO even NSNS operators. Okay. So this operator in particular is a GSO even operator in type 2A theory. So this will be included in the spectrum. Okay. Whereas, and this will not be included in the type 2A spectrum. Whereas in type 2B, this will be part of the spectrum, but this will not be part of the spectrum. So it's the question of how we choose GSO projection on the left moving Raman sector or the anti-holomorphic Raman sector. Okay. That's the only difference.
Thank you.
Is this clear?
Yes, yes.
More questions? Otherwise, we can postpone them to the discussion session of this afternoon.
Okay.
So thanks, Ashok. See you later.
Okay. Thank you. Thank you. Yeah.
Please do not leave the room.
There is one more announcement, one more communication.
Okay. So I'll sign off.
No, you can say yes. Hi. Hi.
Okay. Okay. So see you at 7.
Bye. Bye.
At 7:30 my time, and which is 3 o'clock your time, right?
Yes. Yes. The usual time. Yes.
Yeah. Okay.
Okay. Bye.